This is the first video in section 6.5, tangent planes to level surfaces. Now, first of all, let me explain a little bit about what we mean by a level surface. So, in this context, we have a function of three variables. And so remember, the graph of a function of three variables is four-dimensional. So we have this fourth variable, that's the dependent variable, defined in terms of these three independent variables. So our graph is four-dimensional. Now, when we have a function of two variables, the graph is three-dimensional. And so when we look at a level surface, we hold the z fixed and we slice through the graph and we see a curve. But with a graph of four variables, when we hold the fourth variable fixed, say we'll call it k, and we slice through, so we have the surface, f of x, y, z is equal to some constant k. We slice through at this w equals k level, and what we see is a surface, because we're in three dimensions now. So you have a graph of two variables that's three-dimensional. When you slice it, you see a curve. But when you have a function of three variables, your graph is four-dimensional, so when you slice it, you see a surface. And so the equation of the tangent plane to the level surface at the point x0, y0, z0 has as its normal vector the gradient of f. And so again, it's not a surprise that there's something that we call a tangent, where the derivative, something we call a derivative, gives us a direction. And so the normal vector of the tangent plane is a gradient. Now, then we look at what we call the normal line. Remember, this vector is going to be orthogonal to the plane. So that was a tangent plane. Now we have a normal line. Well, the normal line is the line that goes through this point in the direction of this vector. And so the normal line passes through the point x0, y0, z0, and it's in the direction of the gradient. So let's look at an example. Example 188. It has two parts, A and B, and I did some of the preliminary work here that's common to both parts before I started actually talking about each part separately. So we're looking at this function of three variables. We're looking at the level surface, okay? F, x, y, z is equal to 11, so that's our surface. And we're concentrating on the point 1, 2, 3. So if you substitute 1, 2, 3 in for f, you get 11. But what we're doing is we're taking this graph and we're slicing it at 11, and this gives us a three-dimensional surface. The graph is four-dimensional because it's a function of three variables. The surface is three-dimensional. What do we need for both parts of this? Well, we need the gradient. So we calculate the gradient of the function. We have the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. We want the gradient of f at the point 1, 2, 3. So we simply substitute 1, 2, 3 here, and we get the vector 13, 4, 3. This is our gradient. Now, what did part A ask? Part A asked for the tangent plane to the level surface at the point. So we find the equation of the plane that passes through the point 1, 2, 3 with normal vector 13, 4, 3. So that's the equation of the plane that contains the point 1, 2, 3 with normal vector 13, 4, 3. The normal line is simply the line that passes through the point 1, 2, 3 in the direction of the gradient, which is 13, 4, 3. And I wrote the line as a vector equation. So point 1, 2, 3 in the direction of 13, 4, 3. We could have used the parametric equations just as easily. X is equal to 1 plus 13t. Y would be equal to 2 plus 4t. And z would equal 3 plus 3t.